Okay, and we are recording. I'm trying to get over this habit of saying, and we are live when it's a recording. This is a video, so it's not live. But let's get ready to do some algebra style math, which is going to be about graphing, and it's going to be about the y equals mx plus b form of the straight line equation, an extremely useful thing to know about. When we have y equals mx plus b, the m and the b are actually numbers. But to describe the form we're using, we put these variables m, that means slope, and b, that means the y-intercept. We'll talk more about that. So an example of a straight line equation isn't really this. This is just the form of the equation. An example is this, y equals 2x plus 3. The m and the b can be any numbers. This time they happen to be a 2 and a 3. And we'll talk about what that means. We're going to graph the straight line equation, we're going to make a table of values, and we're going to do a lot of other things to really examine this idea of y equals mx plus b and what it looks like on the graph, what the different parts of the equation mean. Now, it is now November, and it is cold outside, and I'm wearing slippers, but I'm not cold enough to put on a sweater, at least not yet. This jersey is Sunderland, a team that is often in the Premier League in England. They are located in the Newcastle area in the northeast sort of corner of England. And I like this shirt, beautiful shirt. Even the advertisement looks nice. Okay, Mocha, my beautiful assistant, is upstairs. She probably won't be able to appear in this video. There are a lot of people coming to the door today, and I know she will get too excited if that happens. So let's get into the math. I have created a graph. I don't have grid paper on my wall, and I'm not drawing it this time. I did last time. It took a while to draw it and make it look nice. But this time what I want to do is be able to draw graphs quickly and erase them and draw many of them. So I'm not even going to use a ruler. So long as it's fairly straight, it should be good enough. And we have to be careful how we scale our axes so that the math that we're learning makes sense with the pictorial version of it, the graph. Okay, now there's a lot of different things that I want to talk about, but they all involve doing a lot of examples. And it doesn't even really matter to me that much which order I do the examples in. So I'm sort of improvising a little more than usual. I want to graph this. Now, you will remember not too long ago we did plugging. We were working with algebraic expressions and we tried plugging different values in as the x and seeing what answer we would get. Well, we're going to do this. When you have an equation like this one and you want to graph it, you can make a table of values. You can make several points in the table of values, and you will make those points by plugging. The first value I'm going to plug in is going to be x equals 0. So I'm going to do the algebra over here because I have some room over here, but I have to do algebra 3 times. It takes a bit of space. So I'll rewrite y equals 2x plus 3 here, and then I'll make sure it's showing in the video. It shows quite well. I may want to write a little bigger. And if x is equal to 0, then that means I can rewrite this, but I can replace x with a 0. Now, when we see this, we have to realize, okay, the x is gone now. I don't want to keep on drawing an x in my equation. I have substituted, I have plugged. I have plugged that 0 into the x position, and now we're answering the question, well, if x is 0, what is y? But all I have to do to simplify this is first multiply 2 times 0, which gives me 0, and then add 0 plus 3 is equal to 3. So I know students can do this very quickly, and they may not show as many steps as I do, but you should show at least a bit of steps to make sure that whoever's reading your work understands what you're doing. So therefore, if x is 0, that means y is 3, and I can write the 3 over here in my table of values. Writing carefully because I'm kind of writing backwards for me when I do this. Now, we could choose any values we want for x when we're plugging, and in fact, we can even choose values for y and plug into the y position instead. This is one of the reasons we've been working on algebra for so long, because algebra skills allow us to plug a value into either position, the y or the x, and simplify. And I'm going to prove that because these points, these are points which we're going to graph on the system, coordinate system. These points that involve a 0 tend to be very quick to find. So this point 0, 3 that's how I would describe it as a coordinate pair, is the y-intercept. And in fact, it's the b. We were already saying that b means the y-intercept. So we can see that when I choose to plug x equals 0 into the equation, I find the y-intercept right away, and that's useful. But I can also decide to make y equal to 0, and I'm choosing to do that. A lot of times with the plugging, we'll just keep on plugging in on the x side. And then all of this simplification happens over on the right side of the equals, and it is quite simple. But the thing is, if we find the point where y is equal to 0, we're finding the x-intercept. And the x-intercept is also useful, and it's also fairly easy to find because it involves a 0. Let's do that now. Y equals 2x plus 3 turns into 0 equals 2x plus 3. Notice how I write the equation first. Students often don't do that. They just go right ahead into this line where they replace. But when people are just starting to do it, I like to encourage them, every time you do one of the points in a table of values, when you want to do the algebra for it, put the equation down, copy the equation down the way it is, then do your substitution, because it helps remind you what you're doing so that you don't feel like you're lost in the process. Now we're going to do some algebra. We know algebra skills. We have a 0 on the left of the equals. Well, what we'll do is we'll move one of these terms to the other side. Well, how do I do that? If I have 2x over here on the right side of the equals and I'd like to get it over to the left side, I do the opposite. So that 2x I can see is being added to the right side. So I can subtract a 2x from each side. These cancel. We're used to doing this. These are steps in algebra. And we end up with negative 2x. And then, on the right side, all we have is the 3. We're not finished though, our x is not isolated. So since it's being multiplied by a negative 2, we'll divide both sides by a negative 2. These cancel, and x equals negative 3/2, which is a perfectly good answer. Or if we want to switch it into decimal, negative 1.5. So this time I'll choose to turn it into a decimal. X equals negative 1.5, therefore goes here in the table of values. So this algebra has a little bit more steps than that one. And it's not necessarily quite as simple. But it is an algebra exercise that we know how to do because we've been working on our basic algebra skills. So we can do this. I am running out of room for algebras over there. I'm going to do one more. I guess I'll do it here. So I want to choose another number to plug in. I'm going to plug it into the x side because it's faster. But I don't want to choose x equals 0, and I also don't want to choose x equals negative 1.5 because I've already used both of those. So I can choose anything else I want. I think I'm going to choose 1. If x is equal to 1, then y equals 2x plus 3 becomes y equals 2 times 1 plus 3, which is 2 plus 3, which is 5, and I have the y coordinate that goes with the x coordinate of 1. I have the 0.15. Now let's graph. We were practicing graphing, so this is fairly straightforward. 0, 3. So I want 3 to fit. I also want 5 to fit. That helps me decide how I'm scaling my graph. But the way I'm scaling this graph is not going to be very different from the usual because I didn't end up with extremely large or extremely small numbers. So if I do this, I can fit 5. I'll show the 5, I'll show the 1. I don't necessarily label all of them. I just make sure that they're proportional and that the scaling makes sense. And then I want to show negative 1, negative 2, negative 3. I'll show the negative 3 here. And I'm going to show 1, 2, 3. So I'm just doing enough scaling so that I can get everything on there. And I'll show all of those. Negative 1 on the y-axis, negative 2, negative 3. I'll show the negative 3 again here. I have enough showing so that I can plot these points. I can graph these 3 points like we were practicing so much last week. 0, 3, left, right direction. I am going 0, so I'm staying on the y-axis. But the y direction, I'm going up by 3. It is positive 3, 1, 2, 3. So the point 0, 3 is right here. I'm going to label it, but I'm trying to put my labeling of the point so that it's not in the way when I go to draw my line. Then negative 1.50, we were practicing that last week as well. Negative 1 is here, negative 2 is there, so negative 1.5 is halfway between them. And it's staying right on the x-axis because the y-coordinate is 0, so we're not going up or down. Finally, this third point, 1, 5. X is 1, y is 5. And we're able to put a dot. Now we get to talk about, why do we do 3 points? Why did I choose to do 3 points? I could have done more. I could have done as many as I wanted. I could make this table of values 50 points long if I want. I could also have said, oh, I only want to do 2 points. I like these y-intercept and x-intercept. That's enough. I can draw a line if I have 2 points, because it's true. Whenever you have 2 points, you can always draw a line through them. But the reason to have a third point is to catch yourself if you made a mistake. Little mistakes can happen, especially involving negative signs when we're doing this type of algebra. So if you have any 2 points, wherever they land, you can draw a line through them. I can put a point here and a point there, draw a line. I can put a point there and a point there, I can draw a line. You never will see anything wrong with the line you draw. But if you have 3 points, you need the third point to land in line with the others, and that's what happened. So that third point is very helpful for making sure that we feel comfortable with our answer, that we feel confident we didn't make a mistake. And I am not using a ruler, I confess it. I encourage students to use rulers when they do this though. I'm drawing a straight line through the 3 points. I'll finish labeling them. This one is negative 1.50 and this one is 1, 5. I have graphed a straight line. And how do I draw the line? I draw the line right to the end of the graph. You don't want to necessarily have to continue it all the way to the end of the page that you're working on. But if you made your graph this big, the x and y axes this big, then I like to say draw the line right at least to the end where you showed your axes. Because that helps the student prove to whoever's reading the graph after that they understand that this line actually does go forever in both directions. We could find points very far along that direction or very far along this direction if we chose the right numbers to plug into our equation in the table of values. But we chose these 3, and it was enough to fit the line on this graph. We have successfully graphed a line. That's very good. I don't have notes this time. Instead, I'm using my laptop to look at my notes. So I want to go back now. Now that I've done this example, I want to go back and take a look at what we started with. We started with the y equals mx plus b form of the equation, and this is the equation of a straight line. Straight lines will always be able to be expressed in this form, usually, and the number that's in the m position is our slope. We will talk a lot about slope. The number that is in the b position is the y-intercept, and we can see evidence that that is true right now from our example, because 3 is my y-intercept, and the point that has an x-coordinate of 0 is the y-intercept, and here we go, the y-coordinate is 3. So the number that you have in your b position is not only the y-intercept, it's also the number that is the y-coordinate for the y-intercept. The x-coordinate should always be 0. An x-intercept works the same way, except it's the y that's always 0, and then the x-intercept is going to be the number that is in the x position. Okay, then of course, what are y and x? They're variables. And we learned that way at the beginning of algebra, that algebra allows us to work with variables. We get used to thinking of x as our variable, but we can have more than one variable. And in this case, we have 2. The x and the y are both variables. They both can change, and we can see evidence of that in here as well. This x keeps changing depending on what value I plugged in. The y also keeps changing. Okay. The y-intercept is the point where the line crosses the y-axis. We can see that's true as well. So it's interesting because what we see is we have these components of the exercise that we're doing. We have the equation, we have the graph, and we have the table of values. And the 3 of them work together to give you all the information that you need about this straight line. The slope is a special value that has a lot of meaning to it, and I want to talk a lot about the slope in today's lesson. The slope can be expressed with this little phrase, rise over run. And that's kind of interesting. It means that when you are at one of the points on the line and you move to another point that's on the line, the ratio between how high you rise or go down and how far you run to the right will always be the same if it's a straight line. So the rise over run, for instance, we could find the rise and run from this point to that point. So let's do it. From this point, I rise from where y is equal to 3 up to where y is equal to 5. So that is a rise of 2. I'll do it here. From 3 to 5, well, I'm just going to say from 3 to get to 5, I go up by 2. So I'm just going to write 2. And then the run is the same idea, but it's from left-right direction, and we will tend to always do that to the right. So from this point to get to that point, how far to the right did I go? I went 1 unit to the right. I went from where x is equal to 0 to where x is equal to 1. So my run is 1. The rise over run, which is the slope, is equal to 2 over 1. But of course, we all know that 2 over 1 simplifies to 2. So therefore, the slope in this case is 2. But we knew that because we know that m is the slope. So this is what you want to happen. You want the different parts of your straight lines exercise to back each other up, to confirm each other. So playing around with this rise over run thing, I was able to see that my slope was 2. And then I'm not surprised because I already know that m equals 2. And in this straight line equation, the m is replaced by a 2. My slope is 2. 2 over 1 is the same thing as 2. This is interesting. Okay. I think what we need to do now is do some more examples. So it's time for me to do some erasing. I'm going to erase my algebras. I'm going to erase everything. Erase my whole graph. It was pretty, but I need another one now. It's time to draw another graph. Erase my table of values. Erase my other algebras. Erase everything. Okay. So let's do another one. I'll start by drawing a graph. I'll try to make it fairly straight so I won't go too fast. There's my x-axis, there's my y-axis. I use arrows on the right and on the top, and I label them x and y. This is just a good habit to be into, and it is correct form for doing this. Let's do another equation, but I'm going to do it differently. How about y equals 3/4 x plus I'm not going to put a plus. I'm going to put a negative y-intercept this time. So I'll put a minus 3/4 x minus 2. Okay, I want to graph this, and I know how to graph it with a table of values, and I definitely think it's a good thing to do. Graph an equation with this table of values and do that many, many times to practice so that you get a feeling for it and you get good at it. But we also know some other things. We know that our y-intercept should be -2. Yes, the sign, the subtraction sign, goes with the y-intercept. So it's not just a y-intercept of 2. This time it's -2. And we know that our slope is 3/4, 3/4. So that is enough information actually to graph this line. I need to put some scaling on here. So I'm just going to do -1, -2 like this, -3, -4, -5. I'll show -5 here, but I don't want to label too many of these little lines because it would get cluttered. And I will put 1, 2, 3, 4, even 5 fits. I can put a 5 there. And I'm doing the same thing up here. 5, a little bit of a messy 5, -1, -2, -3, -4, even -5, make that a little longer, it all fits. Okay. So I'm showing all the 5s and -5s so we can see how I've scaled my axes. Okay, now, what did we learn? -2 is our y-intercept. Well, we know what happens when we have a y-intercept of -2. It means that here at -2 on the y-axis, we have a point where this line will cross the y-axis, because that's what a y-intercept means. And then we also know that our slope, which we can see as being rise over run, is equal to 3/4. Therefore, we rise by 3 and we run by 4. So I'm going to start from this line, and I'm going to rise by 3, which means I'm going up by 1, 2, 3. That means I am getting up to, I'll show a little arrow, I don't want to make it too dark. I'm getting up to here, and I don't want to draw a point, because I've done the rise, I haven't done the run yet. So I'm not ready to put down a point yet. But I am rising by 3. We can see that this is at the height of -2 along the y-axis. So rising by 3 from -2 is the same as saying -2 plus 3 if you're just working with the numbers. And -2 plus 3 is equal to +1, so it makes perfect sense that my rise of 3 from -2 brings me up to y equals 1. And then my run of 4, I am going to the right by 4. So from here though, I'm not starting here anymore. I've already done my rise, and from the place where my rise brought me, I do a run of 4, which means I'm going to the right by 4 units, which means I am landing right here. I have done the rise over run trick to find a second point that is on this line. Rise by 1, 2, 3, run by 1, 2, 3, 4, I'm double checking, and then I can draw a line through those 2 points, all the way through the graph. I have graphed this line, and I didn't do a table of values. So the form of the equation, the y equals mx plus b form, is extremely useful, because when you have the equation given to you in this form, you know enough information to graph the line without even having to do a table of values. And in fact, once we've practiced this enough, when we see this equation, we don't even have to draw the graph to know a lot about what's happening with this line. I can look at this equation with no graph drawn yet, and I can say, well, I can see that the y-intercept is -2, so I can sort of picture that. And then I can see the rise over run is 3/4, so I picture, okay, that point -2 on the y-axis, rising by 3, running by 4. It tells me that the line is going to be tilted like it is. The way it's tilted, the fact that it's tilted upwards, and how steep the slant is, was given in this combination of rise over run, because that's what slope is. Slope is a description of how the line is tilted. This one is tilted so that it goes up by 3 every time it goes to the right by 4, and we would be able to do the rise over run trick over and over again and keep on finding points further along the line if we wanted to. But as soon as you have 2 points that you can rely on, you can draw the line and you can graph the line. It's a nice feeling of power to look at a straight line equation and already have a feeling for how it's going to look on the graph before you start doing any work. And that is what y equals mx plus b gives us the power to do. That's neat. I'm going to label this. So my y-intercept is 0, -2. And this point, which I never even wrote down or said out loud yet, I can see by reading the graph that it's going to have an x-coordinate of 4 and a y-coordinate of 1. And the point for 1 is on my line. Now let's do a bit of a verification by doing a table of values. Why not? I'll draw a table of values. I'll put 4 points in the table of values this time. And what I'm going to do is I'm going to start by putting in the points that I already know. So the 0, -2, and the 4, 1. Now I can plug in anything I want to find any point. I can try to find the x-intercept, which I know is around here, and I can see it looks like it's landing somewhere between x equals 2 and x equals 3. So that x-intercept is likely to have be a fraction or a decimal, unless I drew my graph really, really crooked. But I think, I wouldn't be surprised if it lands there. But I can also avoid decimals or fractions, maybe. It depends on what the equation allows me to do. I can maybe avoid some decimals or fractions by finding points that land right on those corners of the squares in your grid paper. So let's see if I can do this. How about if I make x equal to 8? Now this isn't going to fit on this graph unless I make it longer in this direction. And you know what? I think for this example I will do that. So I'm just erasing the end of the axis and making it longer. And I'll correctly label it, put my arrow. Therefore 6 will be here, 7 will be there, 8 will be there. I'll show the 8 in my scaling. And I'll show 9 as well. Now if x is equal to 8, I can plug to find out what y would be equal to. Why did I choose an x equal to 8? I can actually have some impact on how this goes when I look at my equation and I can start planning. I can see that if I multiply 3/4 by something that is a multiple of 4, that things will simplify rather cleanly and I can maybe avoid decimals or fractions. So let's try it. Y equals 3/4 x minus 2, but my x is 8, so y equals 3/4 times 8 minus 2. When I multiply 3/4 by 8, I can do some canceling. This, if I cancel a 4, this turns into a 1, that turns into a 2, and I have y equals 3 times 2, which is 6, minus 2, and that is 4. I have a y-coordinate of 4. Let's see if we can graph this. From x equals 8, I am going up by 1, 2, 3, 4 units. I'm trying to do it straight. It's a little hard to do way over here so far from the axis. And I'll put my point, I'll label it 8, 4. And then notice how my line looks like it really does want to go through that point. If it's not perfect, it's because I'm not using a ruler. So I'm starting to feel like, this is interesting. That when I look at my equation and I fill in my table of values, I am able to see that things are working. This is working. I start to feel more confidence in my line because 8, 4 seems to land in line with the other two values. But wait, what about these two? We got both of these points by doing different tricks. We got the 0, -2 point by understanding what the plus b part of the straight line equation's form means. And then we got the 4, 1 point by doing the rise over run trick. So what if I try to find the point where x is equal to 4, but instead of using this trick, I use algebra. I'll write my equation, y equals 3/4 x minus 2. I write it again, but I replace x with 4. And then when I multiply, the 4's will cancel, and I have y equals 3 minus 2, which is 1, messy, which is 1, I need more chalk. Oh look, I got y equal to 1 where x is equal to 4. What I did was I just did the algebra that would produce this point. A point that I already knew because I used the rise over run trick. So one trick reinforces the other. Algebra in the table of values gives me the same result that the rise over run trick does. What about the y-intercept? How about if I try plugging and see how I get, what I get if x is equal to 0? I'll do that up here. Y equals 3/4 x minus 2. If x is 0, I'm replacing the x with a 0. 3/4 times 0 is equal to 0 though. That simplifies quickly. So I have y equals 0 minus 2, y equals -2. I did it again. I got a point that was already in my table of values, but this time I did it with algebra by plugging. The plugging is very powerful. In fact, all of these tricks are very powerful. And it's good to practice all of them a lot so that whenever you're in a situation where you're doing some mathematics that involves this stuff, you have a lot of tools in your toolbox to be able to find out useful information for this situation. Take a look at my time. I've only done 2 equations, and I've gone almost halfway through the planned hour for this lesson. So I need to do some more examples and do them a little bit more quickly because I don't think 2 examples is enough for any student. Okay, I'm just taking a look at my notes. I'm going to make up another equation. I'm going to do a lot of erasing here. Erase all of this stuff, draw another graph, and make up another equation, and start seeing what happens. Every time we change what our m is equal to and what our b is equal to, something a little different can happen. If we make small changes, we make small differences happen. So let's think of something else that can make it look a little different. How about if we have y equals -3x plus 6. Okay, so what's different here? My m is negative. I have a negative slope. I have a negative rise over run. It means a lot of things here. Let's graph. Let's make a graph. Okay, I'm ready. I have to do some scaling. And I'm going to be careful how I do my scaling because I can see, 6 my b is 6. My b is a little bit bigger than the other examples that I did, so I need to do scaling where I can make sure that 6 will show up. So I'm going to put the little lines on my axes a little closer together. 1, 2, 3, 4, 5, 6. Going to need that one, and I can show 7. I'll label the 5, but I labeled it quite small so it doesn't get in the way. How does that look? Boy, does that ever look crooked. It doesn't look crooked when I look at it, but actually when I stand right in front of it, yeah, it does look a little bit crooked. Okay, I'm just going to make the best of it. This is what happens when you're trying to do this sort of math on a chalkboard wall instead of in a piece of graph paper. And yes, it is definitely worth it to have graph paper. 1, 2, 3, 4, 5, 6, 7. Label the 5s again. 1, 2, 3, 4. And the negative 5s. Okay, so it's a little messy, but we can see what we're doing well enough. Now, which trick will I use? I'm going to do the rise over run trick again. I'm going to start with my y-intercept, which is 6. So that means I want a dot right here. And my y-intercept is the point 0, 6. Bit more chalk, please. Now, the rise over run trick, well, the last time I did it, I had a fraction, so you could clearly see the rise and the run. But we all know that if we want negative 3 to be a fraction, we can make it a fraction simply by putting it over a 1. So anytime you have a whole number, an integer like negative 3, as your slope, well, you can turn it into a fraction when you need to if you want to use the rise over run. So therefore, I have a rise of negative 3 and a run of 1. Let's use that to find another point. A rise of negative 3 simply means we're not rising by 3, we're going down by 3 instead. So I go down by 1, 2, 3. I'm at the height of the y is equal to 3. If I labeled that, that's a 3. That's how far I went. And then the run is 1. That's only 1 unit to the right, so that's right over here. And I have a second dot. I can label that dot. I have to read it off the graph. Its x-coordinate is 1. Its y-coordinate is 3. And I can draw a line. I will draw a line. Trying to do a straight line, not so easy to do. Going to the end of the graph, I'm able to graph this. And what's different about it? Instead of tilting upwards, like the first two equations that I used as examples, it tilts downwards. Why? Because the m, the slope, was negative. And this is a pattern that you need to appreciate. When you do enough practice, you will see every time you have a straight line equation with a negative m, it means that the line will tilt downwards instead of upwards. That is a negative slope. And we can think about slope like you do when you're on a bicycle. A positive slope would mean you're going uphill. A negative slope would be like going downhill. So a negative slope, we're going downhill. We can see it. We can draw a little bicycle on this line if we really want to. Let's see what else I want to do here. So the slope, which describes how our line is tilted, does two things. It describes whether it tilts upwards as you read from left to right, or if it tilts downwards like this one. But it also describes whether it tilts very steeply or just in a shallow way. And we see this one's fairly steep. 3 is actually a fairly steep slope. Negative 3 is a fairly steep downward slope. This is tilting down further than my previous example where the slope was 2. 2 is smaller than 3, so the slope is not tilted as much with 2 as it is with 3. Okay, so let's do another example quickly. So I am moving on to doing my examples more quickly. This one didn't take quite so long. Let's test what the patterns that we were noticing. I'll draw X and Y axes. That one started off kind of crooked and then it straightened out along the way. X, Y, oops, messy. So what I'm going to do is I'm going to redraw the top of this so that I can make, oh, the whole thing is quite crooked. I really have to stand right in front of it if I want it to end up being straight. Starting over, Okay, let's see if Doug can develop some skill at drawing. Nice straight up and down axis and a nice left-right axis. I'm sure this has to be a bit better. Okay, so in our previous example we had -3 as our slope. And -3, we saw that's quite a steep slope. So -3, that 3 seems to be a rather large slope. How about if we experiment by trying another one with a negative slope, but I'll make it a fraction. How about -1/4 x? And then I think I'll go back to having a plus here, and I'll put, say, 3. Okay, so let's graph this line. We are going to use the rise over run trick and the y-intercept trick again because they are so useful. It allows us to do this rather quickly. So therefore, the y-intercept, the b, is equal to 3. That means I need 3 to show on my y-axis, so I can put a dot there. So I'll put 1, 2, 3, and 4. I'll label the 4, and I'll put the dot on the 3. And the point 0, 3 is on my line. Now I'm going to use the rise over run trick, and this one's already in the form of a fraction, so that's convenient. Rise over run is equal to -1/4. Now that's where a question can pop up. When we have a negative fraction, does the negative sign go in the numerator or the denominator? When you're just dealing with fractions, that's rather flexible, but when we're doing rise over run, I would suggest that we just keep the negative sign with the numerator. It doesn't mean that they're both negative, and that's a mistake I've seen some students make. That makes their answer go off a little bit. Okay, so my rise is -1. It means I'm going down by 1, which is only this far. I'm only going down by 1 unit in the rise. The run, though, is 4, so I'm going to the right by 4 units, which is way over here. And remember, I'm not going to the right from where the first point was. I do my rise, and then from the spot I get to, I do my run. So I now have another point, and I can draw my line. And I can label that point, which is going to have an x-coordinate of 4 and a y-coordinate of 2. I'm reading those off of the graph. I graphed the line. What happened, though? What's different? We had a positive y-intercept, so where it crosses the y-axis is up here. And we had a fraction slope. 1/4 is very small compared to 3, and the line is tilted much more close to being flat than that previous example. And also the fact that the slope was negative means that it's tilting downwards as we read left to right across our page. All of these patterns are patterns that you can rely on. When you look at an equation, and like I say, you start getting to the point where you look at an equation and you can tell something about what the graph's going to look like just by looking at this before you started building a table of values or doing any of these tricks or drawing the graph at all. You look at it and you're saying, oh, okay, well, I can see where the y-intercept is going to be. I can see how tilted the line's going to be, which is 1/4. It's going to be fairly close to the flat. And I can see whether it's tilted downwards or upwards. A very powerful form of the equation. Let me see here. How about if we have a table of values that shows us some points that are on our line, but we don't see the equation yet? What about that type of question? So my next example, I'm going to start by building a table of values for you, but without showing the equation. So let's see here. X, Y, I'll show 3 points. One of the points I'm going to show is going to be the y-intercept, so I put x equals 0 in there. Now little cogwheels are turning in my head, but I don't want to say things out loud. There's an interesting one. Okay, this is going to work. I have a table of values, so I can graph the line. So any student who has been doing the exercises we've been doing lately already has the skills to do this. And look at me applying my new skill of standing straight in front of it when I draw it so that it doesn't get too messy looking, too crooked looking. Not bad. Okay, I need to scale. And then when I'm deciding how to scale the axes, I look at the numbers. Any numbers I have. So I can look at the equation, and that can help. Looking at a table of values is very helpful because I can see that the biggest numbers I have in the y side of the table, we have -4. And that it is -4, but it's -4. So I want -4 to fit on my graph. And all the other numbers are closer to 0. -2 is closer to 0. So I don't see a -8. I don't see a big number like 6 or 8 on the y side. So if I make my y-axis go -1 like this, -2, -3, -4, and this time I'll label the -1, I want to scale the top of the y-axis the same way. So I'm going to show 1, 2, 3, 4, making sure that it's proportional. Then I look at the x side, and I see a 4 here. The biggest number I see is a 4. There are no negative numbers showing. I see a 2, a 0, a 4. I need 4 to fit, so it's the same thing. I'm going to scale this axis so that 4 will fit. I'll show 1 here. And then -1, -2, -3, -4 will also fit. I'm running out of room for all this labeling, so I'm just going to show, in fact, what I'll do is I'll only show the +1 on the x-axis and the +1 on the y-axis. It gives me enough clues to figure out how this was scaled, and now I can start graphing. 0, -4. The y-intercept is -4. We must be getting good at this now. That means that we're not going left or right from the y-axis. We're staying on the y-axis, and we have to go down by 4 units. So that is to here. I put a dot. 2, -2. To the right by 2, and then down by 2. Put a dot. And 4, 0. To the right by 4, and up, down, I don't go anywhere because its y-coordinate is 0. This is drawn a little bit badly. Yeah, I'd say this dot should have been a little bit further to the right. Make it nice and big so that we can make our line go through it. I can draw my line through, and again, if I use a ruler, this turns out much better. But I managed to graph this line. I may as well label it. Messy, very messy, Doug. Okay, so we've graphed this, and we're able to, do we see our slope? We don't really see our slope because we don't have the equation. If we had the equation, then we would know what the slope was. And then the rise over run thing, usually you do that when you already know the slope that shows in the equation. So the idea of doing that backwards, I don't know if that's that helpful. How are we going to find the slope? We're going to find the slope by doing the slope formula. The slope formula, extremely useful. And that is m equals y2 minus y1 over x2 minus x1. Notice this is not y squared, it's y2. It means 2 points. I need 2 points to fill in the slope formula. Point number 1 will give me my x1 and my y1. Point number 2 will give me my x2 and my y2. I can pick any 2 points that I know that are on the line. But I know 3 points that are on the line. I have a table of values. So I can fill this in. Let's say I use the third point and the second point. y2 is 0 minus y1 is -2. I have to be careful here because there's a minus that's in the formula, and then there's also the negative sign that's in the y-coordinate that I'm plugging in. And the x is 4 minus 2. No negative signs there, but we still have the minus sign that's part of the formula. Well, 0 minus -2 is the same as 0 plus 2, and that's 2. And 4 minus 2 is equal to 2, so I have a slope of 2 over 2. My rise over run is 2 over 2. But I can also simplify this. 2 over 2 simplifies to equal 1. My slope is 1. And I know the y-intercept. So at this point, I can show the whole equation. I did the slope formula, which tells me my slope is 1. Now with a 1 as a numerical coefficient for a variable, we can show it if we want to, but we don't have to. I'm going to show it. Y equals 1x. And then plus what or minus what? That point where x equals 0 answers that question. So I have y equals 1x minus 4. There's my y-intercept. And of course I can see that on the graph as well. If I want, I can write this as y equals x minus 4 because it means the same thing. So I'm able to find the equation of a line if I have a table of values. I can make a graph if I have a table of values. These are the three parts of the theory we're learning about the straight line that work so well together. The equation, the table of values, and the graph. If you know some of it, you can use what you know to figure out the rest of it. So we can take a table of values and make the graph. We can look at the graph and build the table of values. We can take an equation and we can do some plugging and fill in a table of values and then make a graph. We can look at the equation and we can use the y-intercept and this rise over run trick to make a graph without even involving a table of values. We have a lot of tools in our toolbox. This is very powerful for us. Okay. This one might have seemed a little bit easy though, because that slope formula step, which we can count on, we need this formula, we're going to use this formula a lot, that allowed us to figure out our slope. But then we kind of had the y-intercept part of the equation given to us. What if we get a table of values that doesn't include the y-intercept? I'm going to make a table of values that doesn't include it, and we'll see what happens. Okay, here are the little cogwheels are turning again. Let's make a table of values with 3 points in it. Label it x and y. Let me stand right in front of this and draw a y-axis. And then draw an x-axis. Okay, now, what equation do I want to work with without telling the students yet what it is? I was going 2 and then 4 and then I thought I could put a 6, but no, I don't necessarily want to put a 6. So I'll use 8. I have a table of values. I can graph this. I have some fairly large numbers. I have an x equals 8 and a y equals 7, so I have to scale in a way that I can show those. So I'll put I'm going to make this longer. Instead of trying to crowd all of these, the scaling into a smaller space when it's already fairly small on the video, I'll just make this quite a bit longer so that I can make x equals 8 fit. 1, 2, 3, 4, 5, 6, 7, 8. Could have made it bigger. 9, 10. And I'm going to label my 5 and my 10 so that we can see what we're doing. The other side, I just have to scale it the same way. -1, -2, -3, -4, -5, and I'll show that -5. And I'll just go to -8 and I'll stop. And now, the y-axis, I need that 7 to fit. So, 1, 2, 3, 4, 5, 6. I managed to make 7 fit. And I'll put 8, and what I'll do is I'll show the 5 again. And then -1, -2, -3, -4, -5, -6, show -5 again. Okay, I think I have enough to work with so that I can graph this. But the purpose of this exercise is to find the equation. And of course, I don't have to graph it to find the equation because we found the equation using the slope formula. And I don't have to make a graph to do that. I'm still going to graph this though because it's good practice. So x equals 2, y equals 4 puts a point here. X equals 4, y equals 5 puts a point here. A bit more chop, please. X equals 8, y equals 7. This is a little harder to do when we get so far away from both axes, but I think it's pretty good to put a dot here, and now I'm going to draw a line through them. I'm not really sure about whether this part of the line is placed correctly, and if I wanted to be more sure, I would make my table of values bigger and include some points where x is equal to -5 or -6 and see what happens. But this is good enough to visualize our situation. What can we say about the slope and the y-intercept? Those two components of the straight line equation, which we don't know yet, just by looking at the graph though. The graph is a bit powerful to help us sort of predict what answers we're going to get when we find the equation. Well, that y-intercept looks really good to be around 3. I don't know for sure if it's 3 because I drew this without a ruler, but I'm not going to be surprised if the y-intercept is fairly close to 3. And the line is tilted upwards, so I'm expecting a positive slope. But it's not tilted really, really steeply upwards, so I'm expecting a positive slope that's not a very big number. And I don't want to try to predict it more accurately than that, because really, I have other tools that I can use. And the slope formula is a very good tool. M equals y2 minus y1 over x2 minus x1. I use a lot of space just to show the formula, but I think it's a really good idea to show the formula before you start plugging values into it, especially when you're a beginner. Since my line isn't using this part of the coordinate system, I can use a little bit of that space for my calculation. And then which 2 points do I want to use? I can use any 2 points that I know are on the line. I know all 3 of them are on the line. So I'm going to try using the third point 8.7 and the first point 2.4, just because I feel like it. So y2 will be 7, y1 will be 4. And as we do this, and as we practice this, and students should practice this a lot, we look at what happens and we look for areas where it could be confusing. The y's go on top. You need the y's to be on top for this to work. We have to learn that. We have to get used to that, because I have seen students who accidentally put the x's on the top, and that was why their answer ended up being wrong when they were doing all sorts of other steps correctly. And the x2 minus x1 is going to be 8 minus 2. And this is correct, but could I make a mistake there as well? Once you realize you're using 2, 4, and 8, 7, you don't want to go too quickly, because if these two switch positions, then you wouldn't have 0.1 over on the right and 0.2 over on the left. You would have things in the wrong order and you would get a mistake because of that as well. So slow down when you're doing the slope formula and be careful, because there are 4 values to plug in. And it would be easy to make a mistake if you go too fast. 7 minus 4 is 3, and 8 minus 2 is 6. And I have a slope of 3/6, which is correct. And I could say I have a rise of 3 and a run of 6 if I wish. It would be correct, but I can also simplify this fraction, because 3/6 reduces to 1/2. So now I know my equation is going to be y equals 1/2 x plus something. I even know it's going to be plus because I look at my graph and I see that y-intercept is going to be positive. So I'm writing my plus sign. But it looks like it's 3, but I don't know for sure if it's 3, so I'm not going to write a 3 here. I'm going to prove to myself what the y-intercept really is instead of just guessing it by looking at the graph. And I don't have the point where x is equal to 0 in the table of values, which is the what if I started this example with. What if you have a table of values, but you don't have the y-intercept given to you? How do you find it? What I like to do is write y equals half x plus b. I have my slope in position because I found that. And now I have too many variables. I have y, I have x, I have b. That's too many. I want to turn this into something that only has one variable so that I can use algebra to solve for that variable. But the magic, of course, is that the y and the x represent points that are on the line. So long as I choose an x and a y that go together for this line, I can substitute both the y and the x, and then the b is the only variable that's left. But I have to keep an x and a y that actually go together. So if I'm going to use x equals 2, I have to use y equals 4. I can't choose any x and any y. I'm going to use this point in the middle because I didn't use it in the slope formula, so it might be feeling a little bit lonely. The point x equals 4, y equals 5. Let me take a quick look at the time. I am getting close to the end of my planned time slot for this lesson. If x equals 4 and y equals 5, I'm going to replace this x and y with a 4 and a 5. And now b is the only variable, and I can solve for it by doing simplifications with algebra. Half times 4 is 2. If I move this 2 to the other side, I am subtracting a 2 from both sides. So I'm showing all my steps, not trying to show a shortcut. These cancel though, b is isolated, and it's equal to 5 minus 2, which is 3. So it turns out that prediction I made for my graph turned out to be correct. But I don't want to just judge by looking at a graph. I'll get a lot of y-intercepts that are close to the right one without necessarily always getting the exact right y-intercept. But I have my answer now. I can write my equation. Y equals 1/2 x plus 3 turns out to be the equation for this line. And I can also verify. If I've done all of this work and I'm not sure if I did it correctly, I can verify by plugging points that I know into the equation and seeing if I get the numbers that I expect. Very useful. The slope formula is super useful. Sometimes you need this second step to find the y-intercept to finish finding your equation. Sometimes the y-intercept is already given and you have a bit of a shortcut. But we need to practice doing this a lot, and we have to practice doing it without any shortcuts a lot so that we're comfortable with it, so that we always know what to do for every situation. There's not very much time left, so I'm trying to decide what I should do with it. So I think I am going to quickly, given an equation, I'm not going to make up a table of values for this example, I am going to quickly graph a linear inequality, a straight line inequality, meaning instead of an equal sign in the equation, I will have a less than or a greater than. So how about if I have y less than, trying to choose a slope I haven't used yet, 3/2 x plus I'll just put 1. I'm going to make a table of values. I'm going to do it quickly by finding the y-intercept. Oh, well, I already know the y-intercept, don't I? So yes, I can see that as being a shortcut. Since it's in y less than mx plus b form, the b is 1, the y-intercept is 1. Hey, I found a point, so that was quick. I'm going to plug in the x side without trying to plug into the y side. I don't want to overuse that too soon in the process of learning about this. So if x, and I'm going to choose an x of 2 and an x of 4, and I'm doing this with a strategy because I see that my fraction, the slope is a fraction with 2 as a denominator, so if I use even numbers, I'm going to end up being able to simplify more quickly. So let's fill this in. If we have y less than 3/2 x plus 1. Now, when I'm doing this step, when I'm plugging to find the value, I can replace this with an equal sign if I want, or I can show the inequality symbol. I'll keep the inequality symbol there. So if we have y less than 3/2 of 2 plus 1, we end up with these canceling, and I have y less than 3 plus 1, which is y less than 4. I like to think of it as, okay, it would have given me y equals 4 if that had been an equal sign. And that means that 4 is the number that goes here. Doing it again, y less than 3/2. This time my x is 4 plus 1. These cancel, but that leaves a 2 here. I have y less than 6 plus 1, which is y less than 7. And we see patterns. We see that I made my x's go up by 2's, and I see the y's are going up by 3's. I don't want to try to force that to happen, but the equations seem to make it happen by itself. Now I want to graph this. I do have a biggish number like a 7 here on my y-axis. So what I'm going to do is erase and just draw my y-axis a bit longer and putting my x-axis lower so that I can make sure that that 7 fits easily. So 1, 2, 3, 4, 5. Oh, I didn't scale very well at all there, did I? I put them too far apart. 1, 2, 3. This time it's going to fit 4, 5, 6, 7. And I'll show 8 and 9 just because it's fun. And there's my 5 so that I can remember what my scaling is doing. And then I see x is 0, 2, 4. This is not going to be too difficult to fit. 1, 2, 3, 4. I'll show the 4. Okay, let's start graphing. I have a lot of positive numbers here, so I haven't even finished scaling the negative sides of my axes, but I'm going to be able to fit these. 0, 1 goes here. 2, 4 is going to be here. And then 4, 7, I'll go over to this side. 4, 7 is up here. Maybe a little crooked, but that happens when you draw a graph without using a ruler. Students should always use a ruler and grid paper. It really helps to remove the confusion that can happen. I'm going to label the, oh, I made a mistake. 2, 4, not where I put the points are fine. 4, 7, that is a little sloppy. Okay, I made the mistake of drawing the line too quickly. So as you can see, the process that I'm doing, taking this equation, making a table of values and graphing it, isn't really any different than what I had been doing with all the previous examples. So the fact that we had a less than sign instead of an equals wasn't making it any different, but there is a difference, which is when you have an inequality symbol, instead of drawing a line, you will draw a solid line if you have one of these, but you draw a dotted line if you have these. So I have less than. It's not less than or equal to, so I need a dotted line. So I'm drawing the line in the same place as the first one I tried to draw, but I need it to be a dotted line. Why? Because these points are not part of the answer. The points on the line are not part of the answer because of the fact that we don't have the or equal to. And we're going to have to practice that a bit more itself because this is the first example and I've already run out of time for this lesson. So, y equals mx plus b, slope, y-intercept. The meaning of those, rise over run, table of values, plugging to find points, extremely powerful. And then doing a lot of practice so that you get lines that are tilted in all different ways that go through the y-axis in all different places so that you get to see what the equations look like and you get to that point where you look at an equation and you already have a good idea for what the graph will do before you even start drawing it. This is a good place to be. With that, I am finished with my lesson for this week, so goodbye from me, my beautiful assistant, and I will see you next time.